Yeah, thank you for the introduction. So I'm super excited to be here and talk to you guys about type programming. It's been kind of a journey I've been on as I've learned Scala and trying to get better at it coming from a Java background. He mentioned this link does not work in case you were trying to use it. Wi-Fi is not working for me because I'm enslaved to Windows, and part of my punishment is not having Wi-Fi and other things that are good in life. So, but it's my employer supplied one. It's better than what I'll pay for myself. And so normally you could actually follow along and nice things will happen, but that's not going to happen today. So talk about my sort of subtitle is Subspace of Scala. Now, who knows what a subspace is in mathematics? Okay, all of you are going to be confused because that's not what I mean. So I'm actually going to show you what I mean by subspace. It's a kind of an unfortunate overlap of names. It's not the subspace when you're thinking of, say, linear algebra. It's not that. So, but let's move along. Just briefly on myself, just so to kind of give you some context of where I'm coming from. I've already mentioned I did Java. I did Java for too long. I got bored, and fortunately I discovered Scala in 2012. And if you happen to remember, that's when Odersky did his first Coursera offering. And so I took that course and said, hey, this is definitely way better than what I've been doing. I'm excited about this, and I fell in love with it, began using it at my current employer. Eventually changed employers to Mentor Graphics in the small tech town that I live in North Alabama. And eventually convinced them to let us write Scala as well. And that was one of the most fun moves I've made in my career. And then we started using Lyft, and I became a Lyft committer. So a lot of folks not using Lyft anymore. It's kind of the quieting down web application framework in the Scala community, but we're still active and working on it, making it better. So that's what we're using. So enough about me. The problem is, what do I know about type programming? I just told you I come from a Java background and all that. So actually not much. So the great news is I don't know this very well, so my talk is going to be fantastic, right? So seriously though, I've made zero contributions to Shapeless, for instance, because everybody knows Shapeless, like the Swiss Army knife of type programming, right? It's the show-off type programming nearly. I've also not, done cats or even Scalazé, things that are kind of like the generic programming. Now what I have contributed is a lot of cat memes, so that's about as close as I can get to doing some really legit programming in Scala as far as this sort of thing goes. But I'm here to just kind of show you my aha moment, like when it kind of clicked for me, because if you're familiar with my blog, you know I actually have written about this topic for a while. A lot of people found it very helpful and thought, well, I should share that as a talk and see how people enjoy it, and if they can kind of help them come from my background of not being very comfortable with the types and move along. So at some point through that, it hit me what Scala programming is like. It's kind of like this video game. Who remembers this game? It's dating myself a little bit. My t-shirt dates myself falsely. I'm not that old, but I love the band. It's a lot like Mario 2, and if you happen to remember, you'll see where I'm going here in just a moment. So this is your normal value programming. Now if you're here during John's talk, you're kind of familiar with all the hazards of type of programming in general with values, and so here you see Mario at the top. Let me move my mouse pointer out of the way. He's here. There's some good things in life, like a cherry. There are lots of bad things that kill you in life. That's normal value programming for you. And what's kind of cool about the game, though, if you come along, you can grab this first little plant in front of you, and you get this little flask. And I'm calling this your flask of type programming, because who remembers what happens next, right? You throw the flask down, you get a door. And if you don't remember the game, where it goes is to this little place called Subspace, and that's the title of the talk. So what happens, you walk through the door, the world flips over in reverse, like mirror image, the colors change, and there's good things. And now you can't fall down in a hole, so we'll say that's like infinite recursion, so you can still kill yourself here, but at least it's in the compiler. It's not as bad. And but there's some great things you can get. The mushroom here you cannot get in value world. This thing will help you live longer and let you kill more things before they kill you. That's great. And the plants here actually are coins to get new lives, if you can remember that. So there's just some, if you go into this world of type programming, there's these great things you can get to equip yourself to be better in value programming. And it's what kind of, I noticed that. And also, everything's still kind of shaped the same, right? You can still climb the vine, you can still pick up things, you can still go jump and get that cherry. So it doesn't have to be as scary and foreign as you might think it is. And so once that kind of occurred to me, I felt a lot better about the world around me in terms of type programming. And by the way, I'm not going to try to fill up the full time. I know we're kind of crunched for schedules, so I'm going to move. But if you do have a question, don't feel shy to stop me. I'm always happy to answer questions, but I'll try to get some lunch because I know everyone's probably hungry. So a val here. So everybody probably knows what a val is, right? And so when this gets compiled and so forth, conceptually when it runs, what'll happen is when this line of code happens, it'll really the compiler will probably turn this into 6 for us, right? There's probably some optimization. Let's pretend it doesn't do that. And num gets assigned this value of 6. So num as it is hit immediately takes on the value of 6, as opposed to a lazy val, right? It'll happen later, right? As you're running, it sees it, says, oh well, now there's this thing called string. If we ever need to know what that value is, we'll go find it here and store it for later. But it won't actually be evaluated at that time. Whereas the 6 was evaluated and assigned a name immediately, this is evaluated the first time you call string, right? Similarly, further deferred is sort of def. So if you wanted something that gives you a timestamp, you could do something like this. So every time you ask for now, the right-hand side is reevaluated, and you get this value. So all 3 of these are immutable and all those things, but they're different in when they happen, right? The first one's very eager, the second one's lazy, the second one's so lazy you don't even remember what it did last time. Well, what kind of hit me is like, well, you can do this, right? So this is the first type thing I did. Even coming into Scala and not being comfortable with types, it didn't take me long to find this trick, right? If I had this kind of complex thing, I didn't want to repeat it everywhere. It's basically a type def from C. And that is like, yeah, okay, cool. But it turns out, of course, in Scala, it turns out, when you run into something like this, it's probably much, much more generalized than you realize at first. And this is certainly the case for a type assignment like this. And so what has occurred to me is like, well, this is like the other things, except this is assigned very early at compile time, right? So this evaluation on the right, which is trivial evaluation, but it's assigned to this name, my map, at compile time. We can use it in there in that sort of time of the world. So let's go back to our value world. And we're going to talk about the simplest domain ever. So this is where I started my blog series, trying to get my head around this. And so what I first did was create booleans and types. So let's first talk about what booleans look like if you were to make values. Let's pretend the language should not have true false built into boolean type. And so you could do this, right? You got still trait, 2 case objects that extend the still trait. That's my whole universe right there, very trivially. And I want to have a couple of nice operators, right? I want to have a not, so the not will turn false and so forth, and an or. So now I've kind of got this def that returns something else, and I got one that takes a parameter, and we can kind of start playing with that. These are super trivial. True, the not is always false, the or is always true. Nothing exciting to see here, and you can expect what not false is. It's just the opposite in a sense, and then the or always returns that. But what's interesting though is like, now okay, let's look at how we would do this with types, because you can do it. So first, the declaration is slightly different. So let's look on the side by side. So in the light blue is our values, the dark blue is our scary types that we're trying to get comfortable with. And here it's just a difference of keywords, right? The first 2 are the same, and then instead of a case object, you make another still trait, just another type, because a trait is like the definition of a new type, right? And so this is how you would start off. But then let's take a look at what our bool type looks like. So this is where the syntax starts to look different, right? So by convention, I capitalize my types. You don't have to do that. It's just kind of the convention, right? So instead of a colon, we have the arrow colon or the angle bracket colon. And so my type is not, which is a bool type, but I'm not telling you exactly what. And then or takes a parameter, and we're probably loosely used to type parameters. Like if you're like me, you come from Java, you think, well, type parameters that's the thing I'm putting in my collection. But of course, again, it's really a more general idea. And so that's how it looks here. Again, so now you see square brackets instead of round. And again, you see the angle bracket colon. It helps us kind of put these side by side like we did previous slide. And again, the first 2 lines essentially the same, but you see instead of def, we got type. You can capitalize the not if you like the general conventions, but that's optional, of course. The more important thing is the angle bracket that we've introduced. And also with the parameter type, you got the square brackets. So everyone's okay with this so far? All right, awesome. Again, true type. So now we actually have a concrete instantiation, in a sense, a concrete type. And that the true type is Boolean, but there's not the types that were declared in our super type are here actually given a concrete value. So again, trivial, right? Not is false, or is true type. But now we got our syntax, and again, side by side, you see the same thing. Just replace val with type, replace def with type as well. Capitalize if you like that convention, and use square brackets and the less than arrow. So at least for this particular domain, you can do exactly the same thing. Here, once again, false type trivially, true or that, And you can look at side by side, again, see the same thing. It's really, they have the same shape, right? This is what I was kind of getting at with the Mario thing, right? The world's flipped over, things look a little different, but it's still kind of the same, right? Or at least it's possible to be the same. And so another thing I was like, well, if I write all this code, how can I even test this stuff, right? Because I don't know what to do with this, right? I want to make sure my code is good. Well, first off, you just compile, right? It's all compile time stuff. So this is a full test. This is all you need. The only thing it's lacking is a package declaration if you want one. And so inside an object, I get this implicitly magic thing that I'm not even going to pretend I fully understand yet. I'm getting an intuition for how it works, but I'm not going to pretend I can explain that one yet. But if you want to say, hey, I want to know that these two types are equivalent, this is how you do it. You put it inside implicitly, and you put it equal, colon, equal inside there, and things work, right? Or at least it compiles, so I believe it works. So very trivial test here. Just, true type, of course, is trivial itself. Let's look at one that's more interesting. So who has seen the pound lying around in some Scala code that you didn't understand? Well, here it is, right? So true type, pound not. So rather than dot, if you're talking type accessors, use pound. It looks ugly, but it works. So implicitly, true type not is certainly false type. False type not is true type. It works. You can do, of course, the parameters, right? So access the OR with the pound, use your square brackets for the argument, and again, the colon equal, colon equal, and implicitly wrapped around it, and it works, right? These all compile. If you screw one up, it does not compile. It works fantastically. But then the next thing, I was like, well, the whole reason you make types is so it doesn't compile when it's wrong. But how do you write a test suite that doesn't compile, but that's a good thing? Right? It's kind of the reverse of what you usually get. Well, the cool thing is that Shapeless has IllType. Also, if you're more familiar with Scala tests, there is does not type check and does not compile and a few other variants. The big difference before I move on is that this fails at compile time. Scala tests will fail at runtime. So you'll get a runtime failure that, hey, this doesn't compile. But the gist is the string, if it passes the string to the compiler, and the compiler fails, then this macro IllTyped succeeds and you're good. Right? It's hard to get, but the point is you should be able to put in stuff that doesn't compile, which is not great in a way, right? Because I can just put arbitrary string in there. That doesn't compile, of course. So you have to kind of work with it to kind of test your own development sort of thing. Like make sure this thing fails, make sure this thing passes exactly when I think. But sure enough, so true type is not false type. So this string gets passed to the compiler, that fails, therefore IllType compiles. And that's how you can get your false test or your negative test cases. So again, same syntax stuff. I just put string around it. It's very ugly looking, but it does the right thing. And fortunately, your users don't have to look at this because this is in your test code. But honestly, one thing that kind of hit me with this is like, this is kind of ugly. I mean, Scala's all about being elegant, and here we are with this pound and square brackets and all this nasty stuff, and and then add implicitly. But that's fine. That's a test thing. But I'm more talking about the pound and the square brackets. I don't like this because what do we do with our values, right? We would drop the dot and you drop the parentheses. If you have one argument, we got this nice syntax trick that you can drop those and it looks like an operator even though it's really just in a method. Well, the cool thing is there is a syntax trick, but this is how it works. So in values, if you have a method with one argument, you drop the dot, you drop the parentheses, it looks beautiful. With types, the exception is, so rather than one argument method, the exception is two argument type. Means that the name of that type can be put in infix position as an operator. So because my V, and I got that because I have a mathematics background, so when you talk formal logic, you use a V for OR and a upside down V for, and it's not meant to be confused with disjoint from Scala Z. This is a true statement here. This compiles. So you can either put it out front, have two arguments, or you can place it in the middle with just white space or no white space in between, and this will compile to give you the thing that you want. And so, at least in the way we have formed our code so far, this is how you would make it work. You would make yourself an object, a companion object that you can import later, declare your type, and just rename it essentially to the OR. And so now we can actually have that nice looking thing that we just shown a moment ago, the implicitly V of my two types is equivalent to having as an infix operator. So that kind of cleans it up a little bit. That made me feel better about it. All right, so that's two types, right? can we do something more interesting? So fortunately, Scala type system is Turing complete, and we can do some stuff that's really, really interesting. So we're going to do the same exercise as before. We're going to look at values of something, and then we'll talk about how you implement the same in types. So this is the natural numbers, and if you're not familiar with the piano types or natural number definition, and I hope I said it correctly because I'm in Europe and I know he's Italian, and so a lot of people are going to laugh at the American that can't pronounce things if I get it wrong. That you encode natural numbers starting with 0. That's debatable. Mathematicians say it starts at 1, but we'll live with it. You start with 0 as your base case, which you see in the middle, the object. Again, these are values. We're not doing types yet. And the next integer, natural number, is defined as just 1 plus the previous. So you got the base trait, nat, for natural number. We got a plus sign that we're going to define. Again, I got my base case of 0, the object. And then natural next, I use n. So it's not arbitrary n, but next natural number is the one after the previous. So you just recursively construct the numbers. So they kind of give you a view what it looks like. So here's maybe some test code. So the number 1 is the next number after 0, 2 is the next one after 1, and so forth. So this is how you build up your natural numbers recursively. And using the plus operator we just defined, we can use Scala tests like I do here. And 0 plus 1 should equal 1, and so forth. Pretty straightforward. And just to back up just a little bit, notice that the definition of plus, of course, is recursive. Which recursive is like this beautiful like magic to me because I love mathematics, and it's just like I just tell the computer a recursive thing and it does it. It's wonderful. So yeah, the next number, if you add something to me, then that sum is really the next one of that and my previous, and then it just bubbles down until it gets to the base case and magically works. So that was our example, and now let's look at the type version of it. I'm not going to do the line by line, side by side comparison. Same thing happened though. I changed the defs to type. I put square brackets. I put in my angle bracket, and everything else is the same. Now I've got the ugly syntax here. We'll fix that in a moment, but I got previous pound plus that. I don't remember the details of exactly why I put plus here, but it worked out better because I wanted my plus to be an operator, so I used the alphanumerical plus here, right, so that I could use the plus as a binary later. And but it's exactly the same. The nat 0 is going to be when you add anything to me, just return yourself. Then the next one returned to me is just a recursion of my previous plus the thing that's getting passed in. All right, and then here is where I added the plus sign to make it look nice. So same thing we saw before, 2 arguments, and then you can use it as an operator. So now the same little test code we saw previously looks like this now. And so again, 1, 2, 3, that's just incrementing from the previous one. So you can use your implicitly, you can use your IllTyped, whatever you want. You can use the plus sign, and this all works. Everybody okay with this so far? Looking good.
Excuse me.
Yes.
Can you go back to the value definition of nuts? Back. Before this one?
Oh, you go. Oh, so you said value. Yes.
Right.
Sorry, I misunderstood.
Yeah. So what does not and pre not?
Say the question again so I can repeat it.
I now go to the next slide. Whatever you have to call it, right? So not n of not 1 is not 2, but why should be equal to not 1 plus not 1? Not 2 as a subtrap not 1, right?
Yeah, so you could, so he's asking about the recursive, the definition of the top 3 lines. So I don't know if I'm answering your question. Let me try this. You could say nat 2 equals nat n, nat 0. Or you can build them up one at a time like this.
Oh, because when you do the plus, it's recurs down to not 0.
Right.
Okay.
Right. Yes. Yeah. Okay. So yeah, the plus recursion will eventually terminate at nat 0, which will return itself and bubble everything, or return the argument and bubble up. Everybody good now? Awesome. So and that's the same thing that happens with the types. There it is. Again, so when you add something to a nat n, it'll say, well, just defer that down to previous. So it's popped off one nat in, which then that'll pop off the next one and the next one, next one, until it finally hits nat 0. It says, oh, well, the sum's trivial. It's just that. And then it bubbles back up to get your sum. All right. So we looked at all this. Everybody fine now? Looking good? Okay, so the next thing that happened to me going through this, like, okay, I've just made a bunch of types. Who cares, right? Because that was fun. What good is it? Well, I try to think of a real life example that makes sense where you could actually use this and do something kind of nice. So I'm making a vector. Now, I don't mean Scala vector / Java vector, meaning the container that's backed by an array-ish thing. And now I'm talking about a mathematical vector, again, like linear algebra. So you got this thing, it has some length, and if you want to do certain operations, there's some constraints on it, right? So if you want to add two vectors, they have to be the same length for the add to even be defined. So that's what we're going to play with here. So let's say I've got vector. I don't have the power of types to work with. This is maybe how I would implement it. And I'm going to purposefully use linked list implementation here because it works nicely with the types. Not to say you could do it different. You can't do it differently, but it's more straightforward this way. So I've got a vector. They all have a size. The nil has size 0 trivially. The non-empty vector has a head element and a tail, and its size, of course, is just one more than the tail. All right, pretty straightforward the way it looks. And also only ints, and we're not going to parameterize that because it gets kind of ugly. So assume we're only dealing with ints here. So let's beef up our vector a little bit, make a convenience constructor. We'll do the double colon cons operator since that's kind of familiar for linked lists anyway. So trivially, you just, it's the head element plus this, whichever one I am. Then, of course, like I said, let's define vector addition, which is very constrained on the lengths. And again, we still have our size. So this is what it's going to look like in use, right? So I might have a sum. So I've got the vector of 1 and 2, got 3 and 4. Their sum should equal 4, 6. But if I have 1, 2, and 6 like this, I can't do that. So you get like an illegal element exception, illegal argument exception, right? This is what you do in, say, Java, especially. If you don't have any way to type constrain it, then you say, well, at runtime, I say that's bad, go away. And so this is what it would look like. So the nil case, you would require that it is nil, or you could require the size is equal. Either one's just fine. And if require from the Scala default predef, this will throw that exact exception. And similarly, you have your non-empty vector. Again, require the sizes are equal, throw the exception, and that match non-empty vector to get the head, because at this point, if the size is equal to this non-empty vector, you know it's not nil, right? So this is the only pattern you need. And this works, right? So again, thinking recursion here, if I sum my head with his head and I concatenate, create a, form a list with a cons operator with my tail, plus that tail that'll recursively go all the way down to the base case and work things out. However, the compiler complains, right? It doesn't fail, but it does give me a warning. It says, well, you didn't check the nil case. But I can look at this and I'm like, well, it's not going to be nil. What's your problem? But the problem is the compiler doesn't have enough information to infer and reason that that is the case. So this works, but you do get an ugly little warning. So you might have to put in an extra case or a case underscore or something there to make it happy. But I'm not happy because that's not how much code I need. So the cool thing is we look at this, like we validate these sizes at runtime, but at least in our examples, when do we know it? And you really go, actually, I know these things at compile time because I wrote them, like typed them in. I'm not reading them like an arbitrary list off a stream or anything. They're typed in, and these vectors are immutable. So let's do that. Let's validate our links without an illegal runtime exception. So this is what I want my use cases to look like. First two lines exactly the same, but I want my IllType to do the right thing. I want it to fail to compile if I try to write that expression into my code. The cool thing is this is very doable. So let's back up to our vector trait, the base trait we have. So now it's got an argument of type nat for his size. So the vector takes a size natural number. Now if we look at the cons operator, it changes because you're adding one element, so therefore it returns a vector of one more than that size. But the actual value expression here is exactly the same as before. The only difference is I've added the type annotation. And look at def plus though. This is the great thing. I can only accept a vector of the same size. That's the only way it's going to work. Give me one of those vectors and the sum will be the same. So we actually look at the implementations, again, it's actually the same, except now I don't have all that require code. I just throw all that away. I just say, okay, well, me plus that is this. That's the only thing it can be. It's constrained at compile time now. And non-empty vector is crowded looking, so sorry for that. But let's actually go to the bottom and then work to the top. So you can see the plus operator, again, is that vector size. Now this match does not complain, first off. You do not get a pattern match failure because nat 0 can never be size that is nat n of something. Again, I'm going to show why I'm working backwards, but bear with me. It cannot be 0. And so this pattern match passes to type the compilation without warning. Again, this is the same. I don't know why I renamed things. I should have used H and T again. I apologize for the difference. Now, what makes things a little bit not obvious at first is that I have to take the tail as my argument. So non-empty vector takes tail size as argument, not size. The reason is my value arguments are where I need my type. See, I need the type of my tail vector. So what I've said is like, okay, fine, give me that thing here. I'll name it tail size, but I am a vector of the next size up. So I am declaring myself as the correct size. It's just that my case class constructor needs the one less, but I'm still a vector of my proper size. And for convenience, you can go and give it a name that looks clean. So that might be, you might have to look at that a little bit later after the talk to kind of convince yourself that's the way you've got to do it. But it's just because if you give size, you can't express tail because I have no way to say one less. I don't have a subtract or a decrement or a previous operator. So any questions on that? Because it might not be obvious. Or are you just going to live with it? Oh, we do have questions.
Can you explain again why the pattern match is exhaustive?
Yes, thank you. That's a good point. So now that, let's backtrack. So the question is, why is the pattern match exhaustive now? The reason is because if we back up to what I just said, I take a tail size and I say that my size is nat n of tail size. It is not possible for nat n to ever be nil. Right? And that's where it comes, because nil itself is just vector of size or sorry, it's natural number, you know, just done. That's it. It's natural number 0. Nat n can only build on that. So it's not possible to have nat 0 ever expresses nat n of something. There does not exist something to put into nat n to get you nat 0.
Can you go back one slide where 0 was defined?
I'll have to go back a ways to find 0.
No, that one. Okay.
Okay, yeah, the v nil. Yeah.
Okay, cool.
But that's what it is. It just can't find one or express it. It's not possible. So then the compiler goes, well, I guess that's the only case. We're fine. Good now?
Yeah.
Very nice. So what if I only told you the type signature of the next function we're going to implement? Would it work? Would you be able to figure out what it does? So let's take a look at one. Double question mark, because I'm not going to tell you the name. Right? But let's think about what it is based on type signature. So again, the first line's the same. It's just a vector of some size. And what my new function is going to accept is the size of that. And then it's going to take that vector. So you're going to give me a vector and his size, whatever that is. And I will give you a vector that's my size and that size summed up. What might this function do? Concatenate, right? Now you can say, well, it might do shuffle. Well, don't be a jerk when you write code and implement shuffle, you know, like do the right thing. So that's it though, right? You generally, you know, going to think it's going to do the right thing, but it's very powerful that it tells you this, right? Because even if it is shuffle, at least you got a really good idea of what you're going to get back. And so certainly it does end up being concatenate. And again, we can take a look at it. So double plus, that's the same as before. Now you see my nil is so the nil case is if you want to concatenate, it's just trivial that, you know, concatenate an empty list is, or sorry, empty vector, it's just that vector. And then the non-empty one is not too bad either. Because again, so you're going to see that all of these functions are super trivial because of recursion. So the non-empty vector case, it's just like, okay, whatever, just concatenate the tail to that and let it bubble down to the nil case and take care of itself. Everybody okay with that recursion? Like someone keep coming up. I hope you're okay with it. All right, and so this works. So this is a cool thing. So now I can start combining these operators that expect different sizes, and it all type checks and does the right thing. So Now I can take 1, 2, concatenate 3, sum it to 4, 5, 6, and that sum is going to equal 5, 7, 9, and any other messed up combination of that doesn't work will not compile. And so I thought, well, that's really, really cool. Like if I were writing a math library, I might do something like that, right? To make sure all your vectors are the right size. Now I probably wouldn't implement concatenate because that doesn't make sense with vectors, but it was a damn good example, so I used it. All right, so here's the next thing I kind of thought, well, I'm not using values at all, right? I'm just kind of playing and exploring types. Like really, like we could just like type all the things. Why not just make a typed list that the list itself is a type? Okay, everybody okay with that? All right, let's dive in. So here's my type list. I'm going to take my 0, my 1, my 2, and now I've got type nil, just to make sure we're not confused with the previous vector I've implemented. I'm making a type vector now. And say it has size, right? So L pound size is 3 in this case, because I have 1, 2, 3 elements. You can actually do this. Why? I don't know. It's fun. We're going to do it. So here's what your type list might look like. So your type list has a size. Now, unfortunately, it's not a parameter. I tried that, and things got ugly, and I don't want to talk about it because it was kind of horrifying. Really, so long story short, what happens is if I make size a parameter, it messes up my cons operator because cons already takes 2, has to take 2, right? Heads and tail. I can't have a third operator for the size and still have it as an operator infix notation. So it just gets really ugly. So it is doable, but you're not going to make pretty code, and I was upset about that. So I will say we're going to lose our constraints, so I'm making sure sizes are equal for now. But what I did want to play with is like, well, let's encode all this completely in types. It's very doable. So again, T nil, it's trivial, his size is 0. And the concatenate, the size is just one more of the previous one. So that's what your sizes look like. But you can actually start doing some really crazy stuff with these type lists. So first thing I did was reduce. So not 1, 2, and 3, reduce it to 6. So I'm not passing the operator. I'm just going to assume reduce, I mean some reduce. I thought, take it light, one step at a time. So the first thing I want to do is implement a reduce where it's just assumed that it's this summation. And this is what it looks like. So my base rate, no big deal, reduces in that. You look at nil. There's an assumption I make here. Let's just make nil 0. So if you reduce that, you get 0. Again, really, something bad should happen here. But I thought, well, let's just let it slide. Let's play with this a little bit. And reduce of my non-empty, my constructor becomes pretty trivial. I just add head to the rest of it reduced. Again, it's just once you've solved one of these recursion problems, you realize they're all the same. Which is pretty cool. Oh snap, y'all! It is Lambda time. So this is where a lot of stuff really came together for me. So I said, can I make a map? Well, by God, you can. Let's talk about the example and then explain it. I've got list 1 and I've got list 2. I'm going to map over list 1 to get list 2. So I've got 0, 1, 2 in a list. I got 1, 2, 3 in a list. And so I'll take my list 1, map it over this ugly syntax, and it's going to give me list 2. Unfortunately, type lambdas have no syntax, arguably. It's really a hack. But hopefully now that you've seen some of this type programming, the hack makes sense, and it did for me. So if we look at it, you've got a type inside curlies, right? So what is this? Just look at the curly part. That's a structural type, right? So that's the first step, is you make a structural type that the only member is a type. We'll call it F. What do you usually see here? Lambda. Well, that just confuses the hell out of everyone. So I'm going to ask you, if you're programming types, don't use Lambda. It's not on my keyboard, and it looks like magic syntax. It's not. You can use any character here. So I'm using F, because function. That's better than Lambda, damn it. So that's what I'm using. And so I can take an I. It has to be a natural number. I'm going to one-up it, and then I've got to do this more hacking, so I got to put it in parentheses so I can put my pound F. So you just have to sort of structural type your function and then rip it out. But you know what pound F is now, right? It's just go get the type out. So that's how type lambdas had this really ugly syntax, and then we thought we'd be really evil and put a lambda in there just to really make sure you're confused. Well, the good news is it's not that bad. It's just kind of a hack. You got to have a structural type, rip out the lambda or the function. And so this is how it looks. It's ugly, but it works. Unless you use a compiler plugin, it gives you pretty syntax for type lambda. This is how you get your type lambda. So whatever I gets passed in, it's going to one-up it. So take my list one, and every one of these becomes the one higher. So questions that I may not be able to answer. Any? Right, like that? So that just made me feel good. So even I think earlier, maybe, was it John? So it seemed like I saw a type lambda. Maybe it was last night, and I was like, I can read that now. I don't know why it's there, but I can read it. So hopefully that kind of helps you as well. But let's look at the implementation of it. So again, it all fits on one slide. The top one, so map, I take something. I'm not actually saying that it's a nat, but whatever. I take something, and that something, this constructor here, returns another natural number, and it returns a type list. And then, so again, we look at t-nil. Trivially, you can map a function over the nil case, and you get the nil, right? It's still going to be empty. But if you map over the cons, that means I've got a head. So I just apply the f to that first element, and then recursive down to the rest of it. So tail map all my stuff, and it just magically does recursion and works works beautifully. So that's how you can now start making functions of types and pass them around. Is kind of in this form. You just have to say what that function is expected to return if it has one argument. So now, is there questions on this one? Everybody okay?
Yeah, here, sir.
Awesome. So that's kind of how that works. No, that is question. So my hearing's not good, so I'm sorry.
If we abstract away from the, if we remove the type constraint on the age, and we turn the f into a type constructor, will this work, or will the compiler explode?
Okay, so you want to remove which one? The here?
I'd like to remove the age subclass of not there, and therefore remove the not from everywhere. Right? A generic list where I know the size by the typesafe size and map over that.
Right. Maybe. I hadn't tried it.
Okay.
So one thing about this code too, by the way, is I don't know how we're getting the slides and things out exactly, but I have this project is on GitHub, and so really all of this code you can compile and run tests, and all this code is so this is just a Lyft application that I use the code as sources to stick in HTML. So this is the real code. It's not a copy paste. So you can go grab that project, run tests, and manipulate it and play with it. So the answer is I just don't know. I've not tried that. That is an interesting question. But in case you didn't hear it well, he was just asking, though, can we remove the nat from H and make this a little bit more generic? And I think probably possible. I was kind of narrowly focused. So that's a very good question, but I'm just not sure. But you're welcome to play with it. Any questions? Is it good to go? Fantastic. So yes, so that's how we do a map. So I've got one more to show you. We're doing great on time. Like I said, I was going to go a little faster so we could get to lunch. Is that a good move, John?
How fast if you can?
I just need however much time you want me to have left.
6 minutes.
How many?
6.
6? Oh, that's plenty. That's way too much. I'm almost done. Let's look at fold now. Let's really get serious. So this is the last example. So this is good timing. So now I've got this list. I've got 2, 1, 0, and 1 in it. I'm going to fold, right? So and really it's a fold left, to be more precise. This is a fold left. And, or is it a right? Crap, I forgot. But it's a fold left or right. We're going to go one direction, and I'll convince myself which one it is momentarily. Again, it takes a function that takes 2 arguments, and then, of course, a base. An initial value. So we're going to take initial value of 0 in this case. So I'm going to fold. I'm going to collect everything with 0, and I'm going to sum them. So if I fold this, I should get 2 plus 1 plus 0 plus 1, which is 4. And this does compile. This works. This is all good. Again, you've got the kind of ugly syntax, but it's the same if you have 2 parameters. You just comma, here's the next parameter. No problem. And that's what the example looks like. Okay. So this is what the code looks like. Now, it gets a little ugly. Part of it's because it gets too wide to fit on the slide, so I've put some line breaks that may be awkward for you. But let's see if we can work on them together. So one thing I noticed is that if you go to a second parameter, you now have to tell Scala what you expect that parameter type to be. Whereas earlier I just said f of nat, whatever, I didn't care. I noticed you have to do it a little differently. I hadn't explored it to the point I've convinced myself of why that is. So if you play with this, that's I was behooved to do this because the compiler complained until I discovered this was the correct syntax. So it gets a little bit busier. But again, fold, it's pretty straightforward. I just have a natural number I'm taking in. I've got a two parameter function that returns itself another nat. And then, so my cons operator, this is nil. So it returns a trivially. So if I fold an empty list, I just give you the value you started with because it's done. The cons case, again, the type declaration is the same. I've got the A, I've got the two argument function or type constructor. And then it took me a little bit to get untangled here, but this is what you have to do. Just fold the rest of it and then do the function with the head on that result. So that tells me that it bubbles all the way down to the right and then comes back. So I guess that's a fold right. I don't know. Maybe it's a fold right with the commutativity broken. That'd be cool. And but I was using plus, so I didn't think about commutativity. But this is kind of how you implement it, recursively. Again, you just fold the rest of it and then apply the function to the head that you have and whatever the result was. Okay with that? All right, so we're agile. Not only are we functional, we're agile. Is that cool? All right, we're going to do retrospective. So after I kind of worked through all this stuff and prepared to talk with it and all that things, it's like, what did I kind of learn? And so what I kind of saw is, well, types are not just the shape of my objects. That is one thing that they are. It is kind of the shape, but that's not necessarily the only thing that it can be. And in one sense, it's like, if you think about it enough, or maybe if you're clever enough or experienced enough, you can actually kind of expedite computation to compile time. Because basically I'm expediting when I check these sizes, for instance, back on the vector that had integer values, but size was checked. We were checking it, right? In both cases we were checking it. We were just doing it a lot earlier, right? All the way up to compile time. And this guarantees I see the errors as a developer, not my users. It's impossible for me to get those types screwed up on my vector, which is a really nice property. And those type validations propagate, right? The really nice thing is that I went through a lot of trouble to define those types, but if you use my library, you have nothing to do. You just add and double plus and whatever, concatenate, until you see a compiler error you don't understand, and then you open an issue on my GitHub. But that's fine. The point is, if you do the right thing, you got nothing to do. So the benefits kind of propagate through. So I know we're running short on time, but are there any questions, comments, or concerns that you shouldn't use this code? Because you probably shouldn't.
That's all very well and good whenever you know, whenever you have access to something at compile time. But going back to, say, your vector example, what if you have to load a vector from a file and you don't know what size the vector is going to be in advance?
Right, if you don't, so the question is, what if you're getting, say, the vector from a file and you didn't know the size in advance, right? Well, there I would just, obviously you don't know, right? You can't use this for that case. What you would want to use this little library I made up is like, well, if you give, so let's say we're working with vectors of size 3. If you give me a vector size 4, I can't consume that, and that becomes a runtime exception. Not later on when I try to sum it, I get an exception. Right, so you'd have to clean it early and write a function that is typed to say this function will read a file and only return vector of 3 or a list of vectors of 3. You would have to handle that error sometime, but you're right. If you're reading this out of a file, you've got to handle that somewhere. But I would just suggest if you like the library, the approach, you would handle it at the I/O time. Good? Chris?
How far can you push these natural numbers without the compiler exploding? Can you have nat?
I'm glad you asked. So I did this as a workshop, and one of the exercises was to break the compiler. His question is, how long can you go until the compiler breaks? Roughly 1024. We found it. Yeah. Now, if you get really past it, it just never breaks. It just sticks forever. But if you hit around 1024, you will get a stack overflow exception at compile time, because the compiler builds this up recursively and blows its stack up. So it's about 1024. So I'm glad you asked that. It's very limited, but who's got vectors of that size, right? So that's my argument. So yeah, there is very much a limitation to this. So great question. I'm glad you asked. Any more? Who is hungry? All right, so everyone stay in their seat for 2 minutes while I shut down my laptop and head over to the food, and then we'll all be good. So thank you. You can get the slides later. Thank you. Enjoyed having you.